Welcome back, everyone. After lunch, we'll go for an hour, 2 to 3, then we'll have a coffee break again for half hour or something like that. I can't remember, whatever the program says. And then we've got another hour later and then a reception this evening. Okay, so hope you hang around. Over to you again, Spencer. I'm on the, for those of you on Zoom, I'm on the Zoom call again, and I should be able to monitor questions.
Okay. So we'll pick up where we left off, which, where we left off was we had just shown that two graphs generate the same or have the same d-separations, if and only if they have the same skeleton and immoralities. And now we're going to start by establishing the connection between d-separation and conditional independence that motivates talking about d-separation in the first place. And so this comes in the form of a theorem that has two parts, which I described earlier, but I'll remind you. So completeness and soundness, and these are my terms for them, and I'm not totally sure how standard they are. But by completeness, I mean, if something's not d-separated, if x and y are not d-separated by z, then there's some distribution P that's compatible with the graph in which they're not conditionally independent given z. And then there's soundness, which is the other direction, which says any d-separations that you do see in the graph are imply the corresponding conditional independence in any distribution compatible with that graph. So given the amount of time I have, I think I'm going to skip the proof of completeness and come back to it later and just focus on the soundness, which is more involved, but I think also maybe more interesting. So, okay, so let's look at the proof of soundness. So we're going to start by fixing some conditioning set z and some x and y that are d-separated given z. And we don't really need to fix x and y. The important thing is we fix our conditioning set, and we're going to transform our graph via a series of operations into a new graph in which the conditional independence of x and y given z is manifestly evident. And then we're going to argue that any distribution that was compatible with our original graph is also compatible with this new graph. And so any conditional independence in the new graph implies a conditional independence in the latter graph, or in the original graph. And to do this, we need a couple definitions and some setup. So first, we're going to order the vertices in Z according to a topological order. And we're just going to introduce the shorthand. Zj is just the first j z vertices. And we're going to describe a procedure now for modifying the graph. Okay. So first, let me just introduce a piece of terminology. So this procedure is going to have a step where we complete a DAG. And by this, I just mean filling in all the edges that are possible, consistent with some ordering of the DAG. So if I have x, y, z, I complete this DAG by just adding the x to z edge. If I have x, y, z, I can complete it by either adding x to z or z to x, doesn't matter. I'll just talk about completing or a completion of a DAG without specifying with respect to what topological order. It won't matter for our purposes. Okay, so here's the sequence of graphs. So we're going to start with the graph G, and then G0 is just going to be G, where we take all the Z vertices and we complete that subgraph. And then we're going to construct Gj from Gj minus 1 through the following steps. So first, we're going to look at all the ancestors. So Gj is going to be constructed by doing stuff with Zj, the jth Z vertex. So we're going to look at all the ancestors in Gj minus 1 of Zj, and then we're going to remove the other Z vertices. But we're going to look at, so this set Aj is all the ancestors in Gj minus 1 of our chosen Z vertex without all the other Z vertices. And we're going to complete them. Then we're going to flip all the edges in this subgraph. And then we're going to complete the subgraph Aj and the other Z vertices. So this is kind of complicated. Let's look at an example. So let's say this is our initial graph. So the first step to get G0 would be to add all the edges to complete the subgraph on the Z vertices. But here there are only 2 Z vertices and there already exists an edge from Z1 to Z2. So that's trivial in this case. You'll thank me that I only have 2 Z vertices in a second when you see what the result of this looks like. So G is equal to G0 here. Now G1. So I've already I've lumped these steps together, but we take G0, we add an edge between, or we add edges to complete the subgraph on all the ancestors of Z1. So Z1 starts off with ancestors A and B. And we added an edge between A and B, and we chose arbitrarily to add the edge from B to A. And then we flipped all those edges. And then we would need to add edges from all the prior Z vertices into the subgraph. Since Z1's the first Z vertex, you don't have to do anything. So now to get G2, we have to add a whole bunch more edges. So if we look at what are the ancestors of Z2 in this graph, well, we have D, B, and now we also have A. We didn't have this as an ancestor before, but we do now. So we need to add edges from A to D, from A to D, from A to Z2, from B to Z2. I think that's everything. And then we need to flip it all around. And then we need to add edges from Z1 to D in the third step. So it becomes a crazy mess. Anyway, that's the result of doing this process with only 2 Z vertices. You can see why it's going to get incredibly ugly with even more Z vertices. So here's our claim about this construction, which will be useful and basically constitute the proof of the claim in an, it'll almost be all the way to the desired claim. So first, the set Zj, so of the prefix of the Z vertices that we've messed with by the time we finished creating Gj, is upwards closed. That is, it contains all its ancestors. So why is this? Well, we've reversed all the edges from, so inductively, if this is true for J minus 1, by the time we get to J has a bunch of ancestors that we wire up all together, and then we reverse all the edges from ancestors of Zj into Zj. So afterwards, we have no edges into Zj. Right? So if I look at this picture again, after the first step, there are no edges into Z1 because we took all the edges into Z1 and flipped them around. After the second step, there are no edges into Z1 union Z2. That is, the only edge into Z2 comes from Z1 because all the other edges into Z2 we flipped outward. So that's the an informal proof of that proposition, of that item. Okay, our next claim. After we've constructed Gj, the ancestors of Zj union Zj minus 1. So in this case, that would be for G1, that would be the ancestors of Z1 union all the prior Z vertices. after G2. This is the ancestors of Z2 union all the prior Z vertices. There are no edges into this set. And this again follows inductively. We've gotten rid of all the edges into Z1 and all the edges into Z1 in the previous step, excluding other Z vertices. And now in this step, we get rid of all the edges into ancestors from outside ancestors, right? So if I look here, first we observe the set of ancestors of Z2 is upwards closed, right? Excluding Z1. And we've reversed all the edges into, we reversed all the edges from this ancestor set. So there are going to be no edges into the set of ancestors along with the Z vertices. Any edge into this ancestor set must have come from another Z vertex earlier. And so when we look at the ancestors union other Z vertices, there are no incoming edges. So it turns out that in addition, GJ is acyclic. And this is a little bit trickier to see. And I'm not sure it's worth going into detail. So the next thing to observe is that the set of ancestors of Zj, along with the previous Z vertices, is a complete directed subgraph. Right? Every edge that's possible is present, and that's because we first add all the edges between ancestors, and then we add all the edges from the previous Z vertices into all the ancestors, right? So inductively, we're adding all the edges that we can at each step of this procedure. And here's the meaty step and the reason that we're interested in this procedure in the first place. If we have an if and only if X and Y are deseparated by Z in GJ, then they're deseparated in the original graph. So somehow doing this operation preserves deseparation. Exactly, with respect to Z, right? We're doing this operation with respect to a particular choice of conditioning set. If we were to do it with respect to a different choice of conditioning set, then we wouldn't preserve any of it, or we would have no guarantees on the deseparations with respect to this conditioning set. And I'll prove this in a little more detail. But then the final observation is that our original distribution is compatible with this distribution, or sorry, with GJ, the graph we're working with now. So if you buy all of these claims, then it will follow relatively straightforwardly that let's take this for granted for the time being, and I'll show you how this implies the conclusion, and then we'll go back and prove what I think is the most interesting part right here. So let's say, so I want to show you that once we're done with this graph, or once we're done with this process and we look at GK, the final graph, that the ancestors of X intersect the ancestors of Y are contained within Z in this final graph. That is, they meet the the antecedent for this lemma from back in the first session, along with, and moreover, Z is an ancestral set, that is, or an upwards closed set. So applying the lemma from the first part this morning, we can conclude that the probability of Z of X and Y given Z is equal to the probability of X given Z times the probability of Y given Z. So the fact that the ancestors of Z, that Z is upwards closed, this should be evident from the construction. we've always moved, in each step, we take all the ancestors of Z and we reverse the edges, so Z no longer has ancestors, except other Z vertices. So the set of Z vertices is upwards closed. Why is this the case? Why are the ancestors of X intersect ancestors of Y going to be contained in Z when X and Y are de-separated originally? This is the hypothesis we need. We're assuming this. We're going to show that that implies this. And then once we have this, along with this, that Z is upwards closed, which is directly implied here, then we'll get the conditional independence that we want. So why does this original de-separation imply this fact? So assume, for the sake of contradiction, that there existed X star, Y star in X and Y respectively, such that some vertex A not in Z was a common ancestor of X and Y. Yes.
So just for clarity, so ancestor of X intersection ancestor of Y is in the completed graph at the end of it.
Yes. Sorry.
Not in the original graph.
Yeah. So in the original graph, we could have all sorts of crazy things going on. The point of this construction is to kind of move all of our conditioning variables to the top of the graph so that we can easily decompose the distribution over X and Y given these variables into something, well, so that we can much more easily see the conditional independence, right? Yeah, so here, this is all with respect to the final graph. The only thing we're using from the original graph is that we had this de-separation originally. Okay, well, so this is very straightforward, right? All we have to do is observe that if there was some common ancestor that was not in the conditioning set, then the following path would be active in the final graph. This would prove that X and Y are deconnected in the final graph. And if you believe that this construction preserves de-separation, this is not possible. Right. So the meat of this result all comes from showing that this construction preserves de-separation. So I'm going to show you that. Any questions on the basic picture that we're going for? Okay. Use okay. So why does this preserve de-separation? So let's assume that X and Y are deconnected in G, and we'll show that they're deconnected in GJ. So first, by an inductive, or we're proving this inductively, so by the inductive hypothesis, they're deconnected in GJ minus 1. So we just need to show that deconnection is preserved as we go from GJ minus 1 to GJ. So let T J minus 1 be an active trail between X prime, Y prime in GJ minus 1. We want to somehow find another active trail in GJ between these same vertices. That's our current goal. So first observation is that this is still a trail in GJ because when we go from GJ minus 1 to GJ, we just add edges. So every edge that we used in GJ minus 1 is still an edge in GJ. And now everything outside of the ancestors of ZJ is not going to change as we go from GJ minus 1 to GJ, right? Because all we're doing is we're wiring up the ancestors together, flipping some edges, and then doing more stuff with this ancestor set. So we only have to worry about the parts of this trail that go through the ancestors of ZJ. So let's draw a picture. So here's kind of the ancestors of ZJ. And here I'm talking about in the graph GJ minus 1. And so we have some Z vertices over here. We have some ancestors of ZJ without the Z vertices. So let's say TJ minus 1 took an edge into this set, touched some vertex, and then left. These edges, or this section of the trail doesn't contain any edges between vertices in the set. So it's going to be unaffected by doing any transformation within this set. So the only thing we have to worry about is, what if we have a segment of the trail that really spends some time in this set? Is it going to remain active, or is it going to fall apart? So we want to restrict our attention to active trails that actually go through this set. And we want to show that they remain active, or we can find some other active trail to replace them with in GJ. So let's explicitly look at such a trail. Okay, so let's look at a segment of a trail, or of our trail TJ minus 1 that consists of a bunch of vertices in this ancestor set. And then let's pick a maximal length segment. So if it goes through here for 5 vertices and then leaves and then comes back for another 3 vertices, we want to look at the 5 vertex segment and then also the 3 vertex segment. We're going to modify each of those to get something that'll be an active trail in GJ. Okay, so the first observation is, let's give names to this segment. So if this is W and this is U, and U here does not mean hidden variable, it's just a name other than X, Y, or Z. If this is W and this is U, and these are the endpoints of the segment that goes through the ancestors, well, the first thing to observe is there are no edges entering this set, or sorry, by this set, I mean this union, I'll call B. There are no edges in GJ minus 1 entering this set because it's closed under ancestors, because the only ancestors of ZJ are either here or here. So there are no edges entering the set, which means that we know that the trail must point out here and it must point out here. Yes.
What about trail that intersects only by I take it you mean just a second.
Yes. Yeah, so that can't happen because there are no incoming edges into this set. Right, so I can't enter here and then leave the set with an edge in this direction because this vertex would also be in the set. Okay, so another observation is, since this original trail was active and neither W nor U is a collider because they both have outgoing edges in the trail, neither W nor U could have been in Z, our conditioning set. And now in GJ, right, we've added edges between all of the ancestors. And in particular, we've completed this entire subgraph, which means that in GJ, there is an edge either from W to U or from U to W. And so we can take the trail in GJ-1 and just replace this entire segment that went through these ancestors with just a single edge from W to U. And the claim is, because neither W nor U was in the conditioning set itself, and the edges from W to the prior vertex and from U to the next vertex are outgoing, neither W nor U will be a collider in the resulting trail in GJ. And so the resulting trail will be active even as we replace all of these vertices with this. Right, so if we had an active trail in GJ-1, we end up with an active trail in GJ. A much shorter active trail because we've just taken a shortcut through all the ancestors. Yeah. So what about the other direction? How do we know we haven't accidentally introduced a bunch more active trails, and that deseparations in GJ-1 are not preserved in GJ, right? So all we've shown so far is that deconnections are preserved, but we also want to show that deseparations are preserved. Okay, so how do we do that? It's kind of going to be the same argument in reverse. So let TJ now be an active trail in GJ, and let it be a minimal active trail. That is, we can't replace it with any subsequent, we can't find another active trail with using any subsequence of the vertices in this trail. So by the argument immediately preceding, right, if it's a minimal active trail in GJ, then it can't visit more than 2 vertices in this entire segment at a time. Because if it did, we could find a shortcut. Right? By the argument before, whenever we visit 3 or more vertices, we can just take the single edge between the start and end vertex of that segment, and that'll remain an active and will preserve the activeness of the trail. And moreover, well, yeah, and in particular, we end up with, we know that in GJ, any active trail must have, anytime it visits this set, it must do so with a segment that looks like this, basically. So we have some undirected edge, and then between 2 vertices in this section, and then we have an outgoing edge to something not in this set. And so we want to take this trail in GJ and figure out another active trail in GJ-1 that corresponds to it somehow. And so what we're going to do is just replace this shortcut with the full sequence of vertices needed to get from W to U in GJ-1. So remember, W and U are both ancestors of ZJ in GJ-1, which means that in GJ-1, there's some directed path to zj from W, and there's some directed path from U to zj. And so we're going to take our trail, which had to look like this in the section where it was in this set. And we're going to expand out this single edge into two directed paths, one down from W to zj, and the other down from U to zj, at which point we now have a collider, and we condition on zj, and so that'll be active. So this is not totally sufficient because it might not be the case that W and U are independent, in the sense that the path from W to zj might actually go through U, right? Or the path from U to zj might go through W if W and U are both ancestors of zj via the same path. So if it was the case that W had a directed path, I don't know if that's too well, to U, and then just gonna move this slightly to zj. Sorry, this is a U. Then this construction wouldn't work, right? But instead, what we could do is take the W to U path in our original graph, or sorry, take the W to U path directly, and then we have a directed path, and that's still an active segment, right? So I don't want to go into much more detail on this, though everything's spelled out in the handout, but the punchline is we can expand the single edge into a path in Gj-1 that will remain active because we know that W and U are both ancestors of something in the conditioning set, or because the path that we take between W and U is just a directed path, and then we don't have to worry about the conditioning set at all. That's about all. Okay, and so once we've established this, that we preserve deseparation in this construction, then along with the fact that in this final graph, Z is upwards closed set, and if X and Y were deseparated given Z, then all the common ancestors of X and Y are inside Z. We get the conclusion that if X and Y were deseparated from our original graph, they are conditionally independent in our distribution, in any distribution compatible with this new graph. And I claim that our original distribution is compatible with this new graph. So why is that? Right, so I've taken our original graph and I've modified it wildly. So here's the original graph. Why do I know that after changing it to this, a distribution that was compatible with the original graph is still compatible with this? And the reason is the following. In each step, I'm building a complete subgraph on some Z vertex and its ancestors. And a complete subgraph is consistent with every distribution, because I can just factor any distribution according to a complete subgraph by just applying the chain rule. And so as long as I'm making modifications that add edges and to a complete subgraph, I'm guaranteed to be fine, right? I can't inadvertently introduce a conditional independence in this sequence of operations that wasn't present in the original graph, because I add all the edges I can. And then even if I reverse all the edges within this set, that doesn't change anything. I still have a complete subgraph. So all the distribution, so it's consistent with all distributions on that segment. And yeah, the conclusion basically follows from that. So I've and it's kind of interesting to realize that I've shown that X and Y are independent given Z in my original graph. I've also shown the much stronger thing that they're independent in a graph you get by applying this procedure, one of the steps of which is just hooking together all the ancestors of every conditioned variable. So somehow doing this procedure is fine. Like as long as you condition on some variable, you can kind of take all of its ancestors and wire them together. And if you were D separated originally, you won't somehow connect variables. Anyway, that's about all I wanted to say about this proof. The details are all in the handout. Okay. So I'm afraid, yeah, I definitely do not have time to do the other direction of this proof. So I'll move on to the do calculus. But please do take a look at the other direction. I think it's quite nice. Okay, so as I mentioned way back in the beginning, the do calculus is a series of rules for manipulating interventional distributions. So let me remind you of the picture we had at the beginning. So we have some distribution with, or some graph that corresponds to a causal model that we can factor our distribution according to the graph, but the graph might have unobserved variables. And we want to write an interventional distribution in terms of purely observable quantities. So here's the correct expression for, unless I've made another mistake, for the interventional distribution. Sorry, this is the, ignore that derivation because it is incorrect. This is the derivation for the example with a mediating Z variable. So this just syntactically doesn't make any sense here. Sorry about that. So ignoring this line, the only takeaway from this slide is we're going to introduce some new notation. The following notation. So we'll write do X as to mean the intervention in which we've set the variable X to the assignment little x. And we'll use this funny kind of do notation to the right of a conditioning bar in place of this P sub X notation. And as I mentioned before, intervening on X, so if I started with this graph, the graph I'd get after intervening on X is the following graph, is this graph, right? So the graph change that's induced by an intervention is removing all the parents of, removing all edges from parents of intervention variables to those intervention variables. And we'll write G sub X with this bar on top of it to denote this graph. So in this notation, the do operation takes our original graph and replaces it with the graph where we've cut all the parent edges to X. Yeah. Okay, so again, the do calculus is a set of rules for manipulating interventional distributions. So one observation is if our original distribution is compatible with G, then the interventional distribution is going to be compatible with G bar X. I don't have a great name for that, but and so we can use D-separation to reason about interventional distributions. So we can take conditional independencies that are implied by D-separation and use that to manipulate interventional distributions. So let's talk about, so the do calculus consists of 3 rules. The first of which is way simpler than the others. So the first of which characterizes when you can remove an observation from from a probability expression without changing anything. So let's say I'm intervening on X and I'm observing Z and W, and I want to see what the effect that has on, or what the distribution on Y that results is. This says that I can drop the observation of Z so long as Y and Z are d-separated by X and W in the post-intervention graph. So let me just prove this quickly. So this actually is very straightforward. So if Y and Z are d-separated by X and W in the post-intervention graph, then by the soundness of d-separation, we immediately conclude that Y and Z are conditionally independent given X and W in the distribution resulting in the interventional distribution, because this interventional distribution is compatible with this graph post-surgery, right? So I'm directly using the soundness of d-separation to conclude things, or to conclude that I can just drop this Z from this expression. So let me draw an example to illustrate what this might look like. So let's say I have X here, Y here, and Z here, and example. Yeah, sorry, I don't have a great example off the top of my head. Risk coming up with a non-example, so I will move on from that and hopefully come back with examples later. Let me get to a more interesting rule. So this second rule lets us, or characterizes when we can replace interventions with observations without changing the result. And before I prove this rule, I need to introduce one tool that will be useful in the proof of this rule and the third rule, which is the augmented graph. And so the augmented graph, which I'll denote aug G and some set Z, is the graph I get by taking my original graph. I'll just draw an abstract picture for it. And I look at some subset of the vertices Z. And I add new vertices. So if I have Z1, and I add a new vertex, Z1 hat, Zn hat. And it's to be interpreted as follows. So, sorry, the augmented graph corresponds to an augmented causal model. I'll describe the augmented causal model, which will have a graph, an induced graph, which is obtained by just adding Z vertices as follows. So the augmented causal model is the following. For each vertex in, let's see. So if my original model had U, V, F, and some distribution over U, my new model is going to have as vertex set V union Z hat, where Z hat is just a set of additional V vertices, Zi hat for each vertex in Z. And my functions f that determine each of the variables will be unchanged except for the functions corresponding to the z vertices. So f of zi in this modified model will be replaced with some g of zi as follows. So g of zi will take all the inputs that f did. So I'll write this as parents. So okay, let's call this original model M. It'll be the parents in M of zi. Plus, it will have one new parent, which is zi hat. And it will do the following. So zi hat will have domain equal to the domain of zi with one additional value, which is, we'll write epsilon. And the idea behind this is we're going to use zi hat to control whether or not we're intervening on zi. So the value here of g of zi will be just f of zi if zi hat is equal to epsilon. So if this additional variable, which just is some new input attached just to so if z hat 1 is set to epsilon, then z1 does whatever it did before. And if z hat I is not set to epsilon, then zi just adopts the value of z hat. So so what is the augmented graph with respect to, so if I have an original causal model and I augment with respect to z by introducing these additional variables that capture whether or not we're intervening on z, the augmented graph is going to be the graph G with the addition of new vertices z hat and edges from the z hat vertices to the z vertices. And so why introduce this complicated different version of an intervention? Or why introduce these augmented models and then their corresponding graphs? The reason is that we now can transform statements about observations and interventions in the original model into, or we can now express the due calculus in terms of conditional independencies in these augmented models. So as follows. So first claim, which I'll use this other board for. So I can express in the original causal model, the distribution on y given x, or I now have this equality. I can express the original distribution of y given x as the new distribution of y given that this intervention variable is set to epsilon, that is, we're not intervening, and we observe x equal to x. So and I can also express the the interventional distribution as follows: as a conditional probability with respect to this augmented model and augmented graph, right? So the probability of the distribution on y given do x is the same thing as the distribution on y given that I've set these intervention variables to the value x. And now if I can show the conditional independence of some quantity with respect to these intervention variables, that is, if I can show that I have some y given if I can show that this expression is equal to this expression, that is, these two, that because of conditional independence, the value of this intervention variable is irrelevant to computing the probability of y, I've shown that whether or not I intervene makes no difference to the distribution that I obtain. So I realize that was a complicated definition, and I'm not sure how clear that was. Do you have questions, or should I proceed?
Since for this construction, you could assume, well, you are referring to this possibility when you draw the new edge, but in the previous section, we were doing modifications on the graph. It doesn't introduce potentially additional constraints. Or maybe I just don't quite get it.
So the procedure, the graph quantification procedure that I was going through earlier is just a tool of proof to establish the soundness of deseparation. So
and that entire proof does not rely on possibility.
oh,
Is it really?
It does not. I'm not sure. I'd have to think about it a bit more. But deseparation being sound, I think, should not depend on positivity.
But would the proof potentially rely on assumptions? You know, but
Yeah.
perhaps each modification introduces.
Let me get back to you on that. I haven't thought about that particularly. Yes.
So one thing that I totally haven't gotten yet is with this second rule, we changed a condition do Z into just a Z. But one thing I'm not totally clear on is that like I thought that the definition of like I think I'm not getting the do operator because probability of y given do little x I thought was shorthand for probability of y given capital X equal to little x, but it seems that there's a difference between these two things. Can you highlight this difference for me?
Yeah.
again?
So the do operator is the interventional distribution. So this is, we take our original model, we replace the mechanism that computes x as a function of whatever, and we just set it to some constant value, which is different from observing x, because when we observe x, that has implications for other variables, in particular by using Bayes' rule of looking backwards, right? You can figure out that implies things about the predecessors of x.
Awesome.
In the intervention, nothing is implied about predecessors because we have no predecessors anymore.
Great, thank you.
So this augmentation procedure, or this augmentation of models and then the corresponding graphs, is a way of relating interventional distributions and distributions without interventions that doesn't involve doing this graph surgery. We add this extra variable that kind of we set to different values to decide whether we're intervening or not. And then if we can show that some expression is conditionally independent of an intervention variable, that's the same thing as saying the expression doesn't depend on whether or not we intervene. So that's the setup. And we now have enough that I can restate rule 2. And I think we have enough time to prove the equivalence between the interventional formula, the formulation with these additional interventional variables and the formulation without. And the rule will be a straightforward consequence of the version with these interventional variables. So could we bring the slides back up? Oh, yes. Sorry.
This definition, but what is the x hat equals? X hat is just the augmented like interventional variable. I guess I'm not understanding what x hat equals x.
So is that at least visible? If not,
Yeah, it is visible.
okay. So the way these new interventional variables, or these new augmented variables work, is that they take on values from. Sorry, let me. So let's do a simple example. So I have X, Y, U. And for example, we looked at before. So if I wanted to augment with respect to X here, what I do is I add a new variable, which I'll call X hat. And I replace the equation that determined X as a function of U with a new equation, which I'll call G instead of F. Just so G will take as arguments the value now of, so previously X was determined by U. Now G will be determined by U and X hat. And it will, if X hat is set to something other than epsilon, G will just ignore the value of U and just copy X hat. If it's set to epsilon, then G will do what it would have done before. So if our original function was f of u, then it will just do what f did.
So x hat equals x. Equals x.
So
X hat. Okay, got it.
so observing the event x hat equals x is equivalent to intervening and setting x to x. Yeah. So we now have a distribution over a larger set of variables that different settings of this one variable switch us between the interventional distribution on our original set and the non-intervened distribution. So it's a formal device that lets us now we can reason about deseparation in this modified graph, and that will have implications for the equivalence of interventional and observational distributions in the resulting graph. Okay.
I put in the copy.
Yeah, I think this is a good time to break, and we'll come back and prove rule 2 and rule 3 and talk about the ID algorithm after a break.
Thank you. We'll reconvene at 3:30. Coffee is outside, and I think maybe some snacks as well. So take a look. Thanks.